Hi everyone. Today we will talk about how concentrated loads and moments affect shear force and bending moments in beams. In the previous part, we learned how internal forces form inside a beam and how to represent them as the shear force and bending moments. In this part, we will move one step further and study beams under concentrated forces and moments. The goal is to understand how shear force V and bending moment M vary along a beam, means shear force and bending moment diagram, and how they are related to external load or Q as a function of X. We will use the Cut method and equilibrium equations to determine internal forces, and we will explore how concentrated loads or moments cause discontinuities in the shear and moments diagrams. By the end of this lesson, you will know how to draw shear force and bending moments diagrams for beam with concentrated loads and moments, identify jumps in shear diagrams and slope changes in moments diagram, and jump in moment diagram that are related to load and shear and moment through differentiation and integration or area under the curve. Let's begin by reviewing the relationship between uh, load, shear, and bending moments that we talked about in last video. Okay. Today we focus on beam subjected to concentrated force and moments. Our goal is to understand how the shear force and bending moments vary along the beam. We will use the cut methods as I explained you. In this cut method, we consider the imaginary cut at different points of the beam because we are not talking about a specific point. We are talking about the whole part of the beam, means X, for example, change between 0 up to L, and L is the length of the beam, okay? We will use the cut methods and apply equilibrium equations to determine the internal forces. Key points include the relationship between load, shear, and moment. Load means Q, shear moment, as you see here, V, and M as the moments. And we talk about discontinuity and some things. Okay, so here is R1 is support reactions, R2 is support reactions of other supports, F1, F2, F3. Here are concentrated loads, means loads apply in a specific point, not a specific region. Okay, and we want to consider X between 0 and L, and V as a function of X, shear force, and bending moment as a function of X. Okay. In this method, we make an imaginary cut at a distance X. I told you in last slide that X changed between 0 and L along the beam and isolated one side, either left or right, no matter, but by considering sign conventions, okay? At the cut, the internal force are replaced by the shear force. V, as you see here, is shear force. It is shear force, or moments or bending moments. And NB that you see is axial force. We talk about that, but not so applicable for beams. Okay, so internal forces are replaced by shear force V and bending moments M. We then apply static equilibrium. What is a static equilibrium? Means summation of Y. For example, if we consider the left side, left, Which forces apply AY, upward, positive? The next one, minus VB equals 0. So it is summation Fy, okay? Summation M0, but moment should be around the cut point, okay? Should be MB, and this distance is X, for example. VB doesn't have any moment, so it should be minus AY times X equals 0, okay? So we write and apply static equilibrium equations to the free body diagram. Shear force is considered positive if left side we consider should be downward. Look at here. For the left side, positive V should be downward. And bending moment for the left side should be counterclockwise. So for left, it's very important. V should be downward and M should be counterclockwise. For right side means here V should be upward and M should be clockwise. So it is sign conventions that you should consider that for writing the equilibrium equations. Okay. We had this in last video too, but maybe you didn't know the relations and the importance of them so much. Today, we want to talk about as a detail here is the key relationship that you will use in every beam problem. The rate change of the shear with respect to X equals to Q. Means the dV per dx is Q, or vice versa. dV equals Q dx, yeah? So integral of V or change of the V should be area under the load. It's very important and we use it at singularity too. Another equations that we have that V equals dm per dx means the rate of changing moment equals V. So dm is V dx, means change in M equals to area under V. So it is so common. First we have the Q. By finding the integral, we find V, and by finding the integral of V, we can find M. So the change in shear force from A to B is equal to area of the loading diagram between XA and XB, or the change in moment from A is B equal to area under shear force diagram, as I told you, first step, writing loading as a function of X. It's used for singularity. And I talk about the order of them. After that, finding the V, and after that, M. Okay. When we have only concentrated force, between two concentrated loads, shear force remain constant. Means it's easy. We can, for example, here we have supports here, and P is external force, AY, BY are support reaction. We have two techniques, means use the cut methods or shortcut, as I say here. First, I consider the cut method. In cut method, we should consider another cut as soon as we reach to new external load. So here, if this be L, for example, is half L, and it is half L. So how many regions we should consider? Two regions. So X between 0 and L per 2. So here it is an imaginary cut. AY. As you remember, I told that for the left, we considered V in this direction and M counterclockwise. And it is the X, that X change between 0 and half L. If I write summations Fy equals 0, Ay positive minus V equals 0. So V should be Ay. How much for this case, for example, 50 kilonewton, okay? The next region or next part should be between half L and L. So the next, it should be 100 here. Here is 50. And here is V and M. And X is between 0 and half L. Sorry, between half L and L. Oh, okay. Again, 50 positive, upward, 100 negative, minus V, 0. Okay, we go to other side and V should be minus 50. So one way is cut method, but I want teach you and the shortcut because when we have concentrated force, so easy. So between two concentrated loads, shear force remain constant, not change. For example, here is 50 between 0 up to L2 because we don't have any new loading condition. We have negative jump or drop as soon as we reach to downward force. Now P 100 kilonewton is downward. So we have jump downward, drop. How much? As amount of this new. So 50 minus 100 should reach to minus 50. Magnitude jump equals to value of concentrated force. If we have upward force means P instead of be downward, be upward. We have jump forward, not drop. So discontinuity occurs in the shear diagrams at each point exactly at the locations of concentrated load. At the end of the beam, shear force returns to 0. It is for checking that means here we have minus 50 here, yeah? We reach to 50 kilonewton as By. So jump upward, minus 50 plus 50, we should reach to 0. It's very interesting. So when we have concentrated loads, only forces, what happens for the bending moments? Easy peasy again. Do you remember that we have dm equals v dx? So if you write the integral, mx means any x in that interval minus the starting value of that region. I consider that the starting value as m1 equals this integral means vx x minus x1, for example, or dm equals dm per dx equals v. What's the meaning of that? Means change in m equals the area of the v. What is the area? Here, area is the rectangle. Again, for the bending moment, if we have the simply support reactions, we talk about that, not clamp. M starts from 0 and reach to 0. But if we have clamp support, story will change. Means depends to the moment that clamp can tolerate or something. Okay, so for simply support here, moment start from 0. So M here is 0. M at this point means M2, this is M1, so it is M2, it is M1. So M2 minus M1 is the area of this, means the area here is the rectangle. How much? 50 times 5 should be 250. 0 plus 250 should be 250. What is the order of that? Do you remember that we say that the derivative of m is v, so it is linear. The derivative of line should be horizontal line or a step line or something, okay? So reach to 250. We don't have any discontinuity for the bending moment when we reach to the concentrated load. Only we have discontinuity in shear force, not bending moment. But the moment here, that should be 0. We expect here 0. If we don't know that moment here is 0, okay, we consider the moment here M3 and the moment here is M2. M3 minus M2 is the area of here. What is this area? It is under the x-axis, should be minus 50 times 5, it should be minus 25, minus 250. And it is 252, so M3 should be 0 and 0. And we see that the slope of this line is minus 50. Why? Because we had the dm per dx. What is dm? Means the slope of this line, yeah? The slope of the curve. The slope of this line is the v at the region that is 50. So the slope of this line is 50. The slope of this line, according to this equation, should be the v at this line should be minus 50. Another shortcut and trick that I want to teach you here, for when we have external load as a concentrated load, the order of Q we considered minus 1, yeah? If you remember, the V is integral of Q. So the order of V is 1 more than this according to the internal rule. The minus 1 plus 1 is 0. What is 0 order? Means exactly constant, not change, means horizontal, step function, something. And the order of M according to the integral again is 0. Means the integral of 0, for example, the integral is 2x, yeah? The integral of constant should be 1, means the linear. So Q concentrated means this one. V is constant and M linear. Maybe a slope here positive, a slope negative. It depends to the value of B. Okay. Effect of concentrated moment. We talk about concentrated force. Now we want to talk about concentrated moment. When we have concentrated moment is applied at a point, the shear force remain constant. As you see here, we have concentrated moment, but not change in shear force at all, okay? Because no vertical force is added. But the bending moment diagram, however, shows a sudden jump equals to this amount of M. For example, here, M is positive or counterclockwise, but you see that drop. So when we have counterclockwise moments, we have drop in the moment, and if we have the clockwise, we have jump in bending moment. Again, here, you know that the slope of this line equals to the shear force. SF means shear force. Here is ML. So the slope of this line is M per L. So this line equation should be MLX, yeah? And this line is constant, not change here. So the slope of this part should be same as this, or the equation, it is MLX. And you see both of them parallel, means not change, because shear force not change. But only we have jump or discontinuity in M because of the concentrated moment. Okay. Example. Derive the loading, shear force, and bending moment relations for the beam of the follow. I want to solve this problem without using the cut method because it takes time, and it is easy that when we have concentrated force, by look at the loading conditions, we can find that. Okay, here we have R1, R2, external force 200, 100. The first step, finding R1, R2, and it is easy. How? For example, I write moment around this point, O point, for example. It should be minus 200 times 4 minus 100 times 10 plus R2 times 20 equals 0. From here, we find R2. How much? R2 is 90. And we write summation Fy is 0, and we find R1. R1, how much? 210. And R1 is 210. And you see that the summation is 0, 2. Okay, I start from here. If we consider V here, R1 plus, V minus, so V is 210. Okay, I agree, it is 210. As soon as we reach to another concentrated load, jump. If the force downward means drop, 210 minus 200, it should be 10 equals 210 minus 200. Reach to another one. Again, drop because it is downward. 10 minus 100 minus 90. Reach to this. Minus 90 plus 90 is 0. And as we expect, from 0 reach to 0. For bending moment, because it is simply supported beam, start from 0. It is the order of this is 0, so the order should be 1. What's the meaning of 1? Means something times x. What is this? We find this area. What is this area? 210 times 4. 210 times 4 is 840. Okay? And the slope of this line is 210, means 210x. Okay? From here to here, what is this area? Is 10. 10 times this is 6, yeah? 10 times 6, this area is 60. This point should be 840 plus 60 is 900. And unit Newton centimeter. This area is minus 90 area times 10 minus 900. 900 minus 900 will reach to 0. And you see that how easy without using any equations or equilibrium of equations for different parts. If we want to write the cut method, how many regions we should consider? 1. If we want to use the cut method, 1, the first one, 0 and 4. The second region between 4 and 10. The third region, x between 10 and 20. Means several equations we should write, but now without using any of them, by knowing the trick of concentrated force and moments, we draw the shear force and bending moment diagram. Okay, here is examples, moment diagrams. In next slide, I talk about the details again, but I want to show you the applications of the beams, not for civil engineer. And for example, here we have shaft considered as the beam, but it is not 2D, it is 3D. Some forces, for example, 200 and 1000, as you see, in Z directions, and it is the graph of Z direction, yeah. And another 500 and 100, it is in Y direction. That you see the equivalent is, for example, 600, 2000, 1000 here, 1200. And we have the support here, but the reactions of the support is not only in Y direction, it is in Z direction too. Here you see the support reactions in Y, support reaction in Z. So it is bending moment in Y direction, it is bending moment in Z directions. And if you remember from the strength of the materials, we have two moments here. It is in one of them MY is 8,000, one of them is MZ 4,000. And when the moments are applied in two planes, they can combine perpendicular, MY squared plus MZ squared, the root square of that. The M should be 8246 kilonewton per meter. And perpendicular to this moment, it is neutral axis. What's the meaning of this? Means here under the tension, and here be under the maximum compression. As you see here, maximum tension and, sorry, it is the axis of the moments in this direction. Here is the maximum compression, and here is maximum tension, means they are more critical regions here and here. Okay, another examples of the shear moments, shear moments diagram, when we have both of them, means we have concentrated loads and concentrated moments simultaneously. So it is 10 kilonewton, it is 30 kilonewton, it is 20 kilonewton meters, and it is 50 kilonewton meters. For example, it is clockwise, it is counterclockwise. Okay. The first step, we should find the support directions. I name A, B. So AY, you see 7 kilonewton, and BY is 13 kilonewton. For shear force, the first region, V should be this, V downward, 7 downward. So V is minus 7 kilonewton. We reach to this because 10, it is downward, drop minus 7, minus 10, drop. We reach to minus 70. We reach to 30, so jump upward. Minus 17 plus 30, we reach to 13 kilonewton. So it is the shear force, or V, as a function of X. For bending moment, the slope of this line should be from here to here. Should be minus 7x, yeah? But what is the area? Minus 17. Minus 7 times the distance between them times 2 should be minus 14. So we reach to end of this point is this point, minus 70. If I want write the slope of this line, slope of this line is minus 7, minus 7x, okay? Another one, the area, I show different color, this area. So the area of this rectangle is minus 17 times the distance from here to here. It is 2, it is 4, should be 2. Okay. And we find another point. Yeah. Sorry, we reached to this point. It should be 1 because we have concentrated moment here. Times 1. Minus 30, minus 17. Okay, minus 14, minus 17, reach minus 31. Okay, we reach to this moment. This moment caused to what? To jump. How much? Plus 20. If you remember, I told that when we have clockwise, jump, counterclockwise, drop in bending moment. Minus 31 plus 20, the amount of this will reach to minus 11. What is this? This point, it is minus 11. Okay, from here to here, from these 2 points, the slope of the line not change. What is the slope of line? Minus 17. So this line and this line parallel. Again, we find this area, minus 11 minus 17 times 1, minus 21. When we reach this point, the slope of line change because the slope of line here is 13. 13 up to where? Up to we reach to concentrated moment. So 13 from here to here, how much? Should be 2. Should be 2 means minus 28 plus 13 times 2 or 26, we reach to minus 2. It is this point. I'm talking about this one. Because of minus 50 drop, minus 2, minus 50, we reach to minus 52 kilonewton. And finally, we reach to here as 0. Okay. Singularity. Singularity functions are useful for handling discontinuities in loading moments. Today, we only focus on singularity for concentrated loads and moments. The angle bracket indicates whether a force or moment is active at a certain location. By integrating the load function using the singularity notations, we can find the shear force and bending moments along the beam. Okay, so here we only focus on concentrated moments and concentrated force. When we have concentrated moment, the bending moments or concentrated moment, we consider the order -2, means x minus a minus 2 equals 0. What's the meaning? For everywhere except the point that applied to that, it is 0. But when it is at the point A, it is infinity. The integral of -2, it should be the power should be -1, okay? But when we have the concentrated load, the Q or the order, if you remember, I talk about that when we have concentrated load, the order of Q is -1, the order of V -1 more than this 0, the order of M 1 more than as V means 1, as you see here. Q is x minus a minus 1, yeah? The integral of that should be 0, and the integral of 0 should be m, that will be 1. Now, the problem that we solved before, in this video, we want to use the singularity, and it is easy. Look at here. We have one R1 apply at x0, so should be, instead of x minus a, here should be x minus 0, so it is x. It is R1. What is the power? It should be -1. I agree. This 20, it should be -20. At which point apply? 4 and -1. Again, -100. X minus 10 -1. And another, it is R2. X minus 20. Again, the power -1. Okay, you see here exactly what I wrote for you. The integral of that give us shear force. X minus 1, all of -1 convert to 0. Clear? And the integral of 0, all of them convert to 1. We know that V and M at the supports or reactions are equal 0 at x0. It is boundary conditions. It is the simply support something. It is R1, R2, means roller or such as this or roller, for example. Simply support. So V and M at x 0 equals 0. What should we do? So easy. If x be 0, means everything that, for example, x minus 40 and some things will be 0. Substitute here for finding V and R1 and R2, yeah? So after that, writing for M, for another equations, and we can find R1 and R2. When find R1 and R2 for each part, we can use the same equations for finding the, for example, the shear force. I start by when x between 0 and 4, okay? For example, when x between 0 and 4, what happens? Back to here. Everywhere is, for example, for V is 0 except when we are exactly at that point, yeah? Or for M, everywhere is 0 only when we are at the exact point that the concentrated moment apply, yeah? And here, when the power is 0. When the power is 0, that you see works for this after integral. Before a is 0, but after a is 1, yeah? Or for the ramp, before that is 0, after that should be exactly the equations of x minus a. Okay, back to here. For v, it is 0 or shear force. What's the meaning that? Means when we are between 0 and 4, not reach to this, not reach to this, not reach to this. The only V that been left should be R1. That the R1 here is 210. So what about M? For M, we use this equation. I told that when x between 0 and 4 means not reach to this 4, not reach to this term will be 0. The only this term will be left and should be R1x. So it should be 210x. As you see from previous slide, it is 210x and it is 210 for B. And we use this equation because after integral of that, we reach to this term and we reach to this term. Okay. This concludes our discussion on the beams with concentrated force and moment. We have seen how to apply the cut method. Yes, use equilibrium equation or EOE and interpret discontinuities in shears and bending moment. You have seen that we have discontinuity in shear diagram as soon as we reach to concentrated loads, and we have discontinuities in bending moment as we have we reach to concentrated moments. And we talk about the order or some things, the derivative, the integral, the relations between Q, V, M. And at the end of that, we talk about the singularity that reach us to same equations of cut methods, but easier than that. And in the next part, we will extend this idea to distributed loads and complex loading conditions, not only the uniform distributed loads. We talk about uniform, we have about triangular distributed load or the order more than 2 or some things. And we will learn how distributed loads influence the shape of shear force and bending moments diagrams, and how singularity functions make it easier to handle combined loading cases. If you found this lesson useful, please like, comment, and subscribe to this channel, MechTalks 2025. Click the next video link on the screen to continue learning about distributed and complex loadings in beam that is classified in stress analysis in beam. Thank you so much. Have a good one and bye-bye.